Hey everyone, welcome to a new set of presentations for those of you who are prepping for the CSCS exam, the certification exam for the Certified Strength and Conditioning Specialist certification through the NSCA. This is the Chapter 1 information that you'll gather so that you can start your process of getting down to more deeper, more applied information later on. So this here is basically a review of how the body systems function, whether it be the nervous system, the skeletal muscle, the skeletal system, the muscular system, the respiratory system. So there's going to be a lot of systems involved here. Short spurts of information that if you took an exercise physiology class is really just basically a refresher. So let's dive right in. But this is coming right out of the essentials information. So let's just keep on trucking here. So the first part we talk about is a skeletal system, which basically we're referring to as a leverage supporter, a leverage mechanism, a supporting mechanism, and a protective mechanism of major organs. This skeletal system that we refer to on average with majority of people in the world has 206 bones, but understand that with fusion, with bones fusing together, that can change that number per person. With injury, with if there's a vertebrae that has to be removed, whatever, an amputee, that can change that number, but understand that we're talking about 206 bones. We talked about what they provide with that leverage, support, and protection. And what is their job is to be pulled upon by muscles to allow for you to push or pull against items or objects and be able to move about, move things, do what you have to do on a daily basis. So if you look to the right on that skeletal, the skeleton, you'll see the major areas that you should understand those locations, what they are, what they do, and then we'll dive a little bit deeper into the skeletal system, to kind of give a little bit more of that information that you're going to need to know for testing. So the first part is looking here, you're talking about the axial. So the axis center. So basically from your head through your vertebrae, and then with the ribs and sternum, that would be your axial. And then all other more limb-based items are more of what we call are what we call the appendicular skeleton. So there we go, back to that information. Axial consisting of the skull, the vertebral column, C1 all the way down to our tail or the coccyx, and then the ribs and the sternum. Whereas the appendicular, we're talking more about the shoulder girdle with the offshoots of the bones of your arms, wrists, and hands. And then you have your pelvic girdle, and then the offshoots of that are the bones of the legs, ankles, and the feet. So movement based versus axis of rotation base. And that's really the main difference. And that's kind of how you want to talk about it to yourself. Axial, think about axis. Well, what rotates, what do we rotate off of? And I mean, our head is on a swivel anyway, so there's your axis anyway. But from the head down to the coccyx, and then the offshoot of the ribs and sternum, and then also your appendicular being more limb-based, like we talked about, shoulder girdle, pelvic girdle, and then the offshoot of each one of those areas. So when we talk about types of joints, there are 6 based ones right here with some examples: fibrous, cartilaginous, synovial, uni, bi, and multi-axial. Now, they're not separated for any particular reason. It's just, just to kind of give you an idea as to the names and how, on the right-hand side here, the axial based uni, bi, and multi, you're basically just saying here that they're the same reference, except they work around either one axis, 2 axis, or 3 axes. And then you got the examples of each there. Now, fibrous, meaning, virtually no movement, sutures of your skull. Pull the skin off of your skull there and look down at someone's, the bony area of your skull, and you'll see sutures, marks where they're, basically like stitched together. Those are your sutures. Those are joints, which is kind of weird, but they really are joints. And so because of that, they are non-movable. We don't want those areas to move. Now, can they adjust based on pressure within the skull? Sure, but they're not moving. Cartilaginous allows for limited movement, and that's intervertebral joints. That's where, you have the connection point where, there's the disc in there and the nerves that come out from the side. Those are your intervertebral areas. Those are limited in movement, although they do provide a mass amount of movement when we have to move ourselves, like if we want to reach down and touch our toes, etc. Synovial, this is our considerably high level movement joints. And these are the ones that we refer to as our moving joints. So synovial joints, usually there's different types of synovial joints that you want to pay attention to. They give you two examples of hinge joints here. Hinge joints meaning that they kind of open and close, kind of like a door. These are your elbows and knees. Now, with synovial joints, understand that you're going to see, like saddle joints, I just said hinge joints, ball and socket joints. Those are just a couple of the examples that we refer to synovial joints, but those are not skeletal system joints that we're referring to. They are synovial joints. So just don't get yourself confused on a test if it asks you, is this, it's a type of synovial joint, not the synovial joint. And then on the right-hand side, like I said, uni, bi, and multi-axial. And they give you the examples there of how you would rotate around one axis, like the elbow, two axes, two perpendicular axes is like your ankle or your wrist, and then three would be like your shoulder and your hip. So what does that tell you? Your elbow can move, but it's usually more one-dimensional. Biaxial, your ankle and wrist, they can work off of two different directions, and then shoulder and hip can move off of three different directions. So you could, and that just by moving those joints you can tell the difference. Moving from there to your vertebral column, the way that I usually explain this to everybody, and just kind of go back to the old way of how people used to eat: 7, 12, and 5, right? You used to think about this. Everybody used to eat breakfast at 7 in the morning. Well, not everybody, but you get the idea. And so what we're looking at here is the adage of breakfast at 7 cervical spines, the vertebrae. People eat lunch at noon or 12. There are 12 thoracic or midpoint vertebrae. And then normally people used to eat dinner at 5. So, dinner at 5, you have 5 lumbar. And so those are the three major areas, cervical, thoracic, and lumbar, that make up the majority of our complete, vertebral column or spine. But understand that there are others too. So you have your sacral vertebrae, which make up 5, which basically your sacral vertebrae are what your pelvis is made of. And then your coccygeal vertebrae, or like your coccyx, that's the extension off of the pelvis. And normally with that, it says 3 to 5 because that's what I was talking to you about before. 3 to 5 because of the fusion effect. Everybody has different numbers there because of a specific fusion. So what do we say? 7, 12, 5. And then for sacral, you have 5. And for coccygeal, you have 3 to 5. And make sure you can differentiate the differences between them, or, so that you can understand how that works. Now, they also give you, on the right side picture, they give you how, the curvature works. If you notice, your cervical spine is more of a concave and more of a curvature inward. Thoracic curve is more of a convex, or more of a curving outward. And then the same thing with the lumbar, more concave. And then your sacrum kind of does that slight convex outward as your coccygeal kind of comes back in. So it's a in, and then out. Really, if you want to, those are your curvatures. So that's where we talk about posture and excessive curvatures in those areas. That's where we refer to for that. Moving from the skeletal system, let's dive into the muscular system, and we'll start off by basically going over the macro and micro structures, kind of understanding how the muscular system is broken down and then why it provides movement. So understanding that your skeletal muscle isn't just a muscle and that's it. Understand that there's also it's really made up of the muscle tissue, the connective tissue, the nerves, and that supply the muscle, and then the blood vessels that supply blood to the muscles. So that's what we're referring to, is that's everything. So a skeletal muscle, yeah, it's the muscle, but there's other components to it. And don't forget to consider that if there is a test that's, on a test question. Also, like it's talking about here, fibrous connective tissues like the epimysium. That's going to be what it says here, covers the body's more than 430 skeletal muscles. So that epimysium is the covering of that, and this is where we'll start to break it down. If you notice at the very top here, epimysium, called the deep fascia. Deep fascia meaning that is the covering of the muscles, and when you get tight muscles, fascia can be problematic in breaking up, so that you can loosen up the connective fibers to allow them to move more freely. Now, the muscle belly, that's what we're talking about here, and then the epimysium is the covering of that. And then from there, if you look down on the bottom to the, down here to the right, you'll see epimysium, the outer layer. Then what you have is a next breakdown of your fasciculus, or one of these bundles, which is covered by your perimysium. So that covering of the fasciculi is the perimysium, which is the next step lower. So you have a big muscle, and then you break down into a fasciculus, which is a basic level of bundles of muscle fibers surrounded by your perimysium. And then you have your endomysium, which is not the smallest one here, but if you follow my mouse, you'll see right in the middle here, this would be your endomysium, which is covered by, which is basically your single muscle fiber that's pulled out from the perimysium. And got your sarcolemma, that covering around each, the covering around each is your sarcoplasm, or the inner fluid is your sarcoplasm. The sarcolemma is that single muscle fiber covering. And then within there, you'll notice there's the nucleus. And then from there, you have that breakdown of a single fiber strand, or a myofibril. That's, and those small myofilaments are the smallest acting mechanical components of the muscle. They are the smallest protein-based moving mechanical parts to your muscle. And that's where you get down to one step lower. Now, when we go one step lower, we'll get to that in a little bit, but understand epimysium, perimysium, endomysium, and then from there, you break it down into your myofibril to your myofilaments. And that's going from macro to micro. And everything in between here, nucleus, yes, each fiber has, can be single or multi-nuclei, so that, it depends on what is required, which muscle you're talking about, and how many, are in each one. But, depending upon the size, will provide more fibers, so on and so forth. The smaller the muscle, the less fibers. So when we go back, right, this is your muscle. We have to understand that this muscle just doesn't move on its own. So we have to supply a nerve, or multiple nerves, or multiple nerve endings to that area. So it just depends on how many nerve endings are being sent down to connect to the muscle, and then therefore you can have motor units. Now, typically there's two types. There's a type 1 and a type 2 motor unit. Type 1 being more aerobic based, and type 2 being more of that anaerobic base that's more explosive. Now, there are many fibers that can connect to one single motor, that there can be multiple fibers that can be related to, that one nerve. So that one nerve can supply many muscle fibers, or that one nerve can supply a very small amount of muscle fibers. And that really comes down to the muscle size and the coordinated effort of that. So for example, your eyes, right? Your eyes will have a very small amount of muscles, fibers, that will be controlled by the one nerve. So you'll have a smaller, more close, it's closer to a 1-to-1 ratio. It's not exactly 1-to-1. Whereas something like your, your vastus lateralis, right? Your vastus lateralis, one of your quad muscles, that right there will have more muscle fibers per one unit, per more muscle fibers per one nerve because that nerve can supply them out. Your eyes are a little bit more coordinated in effort and they require a little bit more fine-tuned motor work. So that's typically why that can happen. But understand that one single motor unit, the muscle fibers and the nerve that innervate it, that can be several hundred to very small. That's what we're looking for there. So let's go back to a couple of pictures ago, and we said there's your myofibril. Well, here's your true, that's that muscle fiber. Well, there it is broken down. Okay, this is your sectional view. Now, if you notice, this is the sarcolemma, the surrounding of that one fiber with all of the myofibrils within it. Now, within that, you'll have a bunch of things. There's your mitochondria. There's these things called T-tubules. We'll talk about those in a second. But the sarcoplasmic reticulum, which is that meshwork that surrounds the whole lot of those myofibrils, because that is where, and these T-tubules are where conduction takes place. So what happens here is that when we have a muscle fiber that needs to be excited, the sarcoplasmic reticulum holds on to calcium. Well, when that nerve sends that electrical effect into the muscle, it will release that calcium out of the sarcoplasmic reticulum into those myofibril areas, and it will excite and allow for these two things to start doing their job, the myosin and the actin. Myosin and actin. Myosin being more of your thick, or I want to say if in this picture here, it would be more of the pink base, where the actin is the thin, more green orientation. Those are your thick and thin filaments. And so on a test question, if it says the thick filament that arranges within a skeletal muscle that shows a striation appearance you would say myosin. And that's how we would break it down. Now, within that, there are a lot of different structures that come with it, and we'll talk about those in a second. You'll see here the M line, the Z line. The Z line is one of the major areas that we want to really kind of understand, because that Z line is where, you'll have these two Z lines come together, and that will indicate whether you're in a contracted or a relaxative state. But we'll talk about that in a little bit. But this is the breakdown even more. If you need to, just pause and zoom in, go for it so you can see the structures a little bit better. But remember, myosin is the thick filament, and it's got those heads on it, and actin being the thin filament where the myosin will eventually make connection to it. So I kind of got into this a little bit before the key point, but just remember that once that discharge of an action potential from a nerve is signaled, it will release calcium from the sarcoplasmic reticulum into the myofibrils, and that's where you'll start to get that tension development or that mechanical force that begins to happen. So from there, we have all these things, these structures, the myosin and the actin. We have more structures of that muscle fiber itself, and then even bigger structures at the macro level. And these need to operate all the time when we're in movement, especially during exercise. So what do we got to know? We got to know about the sliding filament theory, understanding that what happens is the Z lines, and if we go back that picture, the Z lines here in the middle of the cylinder, all right, or the actin and myosin of the myofibril, or the myofilaments, those right there, those Z lines from one Z line to the right and the middle Z line, if we have a contraction, those Z lines will actually shorten and come closer together. And so what you end up with is filaments that connect to each other. The myosin will connect to the actin, and it will basically create a ratcheting effect where it'll bring the Z lines closer together. Kind of like if some of you, and if you don't remember, you can look it up, but Rock'em Sock'em Robots, where you used to punch up and they used to punch up and punch down. Well, that's the same premise that happens with myosin. When it gets excited, will punch up and connect to actin and pull forward. Another arm will punch up and pull forward, and then one will release, another will release, and they'll punch up again. And they're constantly doing that back and forth to provide movement. So it's like, it's kind of like a factory where you have the assembly line of all these myosins that are punching up and punching in, basically punching into the actin, and they're pulling the Z lines closer. So in this sense right here, there's your Z lines right here to the left and to the right, and they are in a rested state. All right, there's either there's low to no force in this positioning. Why do you say that? Because there's no connection between the myosin to the actin heads, and the Z lines are pretty well, outward. So what happens? There becomes a change. This here is partial, all right, and you notice that the Z lines from A to B have shrunk down. It doesn't show you particularly that the heads are connecting, but they do. And what that shows you is a partially contracted motion. And if you notice that the Z lines are coming together, so what's that mean? The H zone is becoming shortened, and so are the eyes. The eye zones, the eye bands are also being shortened because you're getting this closer effect, this pull effect. Because then when you end up in a fully contracted state, you'll see here that you have really close Z lines. You have what we call now that A band. All right, if you notice the A band, if you see where it is, it's the ends of the myosin. They are now completely to the point where Z lines are now basically touching and creating in those A band areas. And that's where we would have a complete contraction. All right. Now we have to realize this continuously happens over and over again. So it has to happen very quickly and very repeatedly. So you're always kind of going through an ebb and flow of how these myofibrils contract. Very quick, definitely pay attention to the key terms that are located in your book, because that'll help to drive home this information, and you'll see these pictures related to that. So with that, like we talked about, there's a resting phase. We have what's called an excitation, contraction, coupling phase, a contraction phase, a recharge phase, and a relaxation phase. And that's what you're always going through is those, rested all the way through to the contracted, then back to your relaxation. So you're always kind of moving, and then I'm went a little bit too far. So we start there resting, contraction, and back, and see how you're always moving in that animated fashion. And that's what's always going on and happening consistently so that the body can provide a really coordinated effort of movement. Now, a person who is new to exercise, this won't happen as streamlined as this, but it can. But taking into account those phases, everybody will move through them differently depending upon your level of experience with movement. And, so a baby versus an adult, then moving past the adult phase back into the elderly phase, you kind of go through this low to high, and then you kind of fall back down again. So, the muscular system, the more you use it, the more it'll stay more coordinated. The less you use it, the more uncoordinated it'll get. So what do we want to have for some takeaway here? The number of cross bridges that are formed between actin and myosin at any instance in time dictates the force production. So if we see here all these cross bridges, well, there's only a few listed right here, but understand that throughout the whole muscle, there are a lot that can be basically cross-bridged, if you want to talk about that. So that makes a big difference, and it'll help you to be able to have more coordinated effort. That becomes really, really important for force production. If you can constantly get those cross bridges to be formed through actin and myosin, then you can have a better force output, meaning that you're going to be able to do things quicker, stronger, faster, whatever way you want to talk about it. Then calcium, which we talked about, and we go back to that picture right here. Remember, calcium is being released out of the yellow, the sarcoplasmic reticulum. So if we go back to that statement, calcium and ATP are necessary. So ATP meaning your energy currency. Without calcium being in there to change the electrical charge, and without ATP present, you will not have any movement. Remember, we have to have ATP broken down and then built back up. Broken down and built back up. And that makes it this vicious cycle of movement that we talk about. So moving from just your muscular system to the neuromuscular system, we kind of talked about motor units, but understand that we have to have this activation of muscles that occurs, and without the nerve, you will not have that activation. So we have to have an action potential. And that's this first part over here on the left. The arrival of the action potential at the nerve terminal will cause what we call a release of acetylcholine inside of our system. Now, that's a neurotransmitter, acetylcholine. And if enough acetylcholine is released, what will happen is you will have, and I'll go up to here, that action potential will cause acetylcholine to cross over into that fiber, into that muscle, and basically be able to start its job, to start its functioning. Because then you will allow for really a electrical change to a chemical change that occurs to allow a mechanical movement to happen. And that's when the fibers will start to contract. And if we go over here, the extent of control of a muscle depends on the number of muscle fibers within each motor unit. And this is kind of when I was talking about your eyes versus your vastus lateralis, your quad muscle. If there are many fibers to a particular unit, and you only have the one nerve that supplies it, it can become more challenging and it'll become more fatiguing. So like it says here, muscles that function with great precision may only have as few as one muscle fiber per motor unit, which is what I was saying about like your eyes. Muscles that require less precision now doesn't mean that it's not precision. It just means that it's more gross movement patterns will have several hundred fibers per one motor neuron, which makes a big difference. And that's what I was saying versus, your eyes, they can blink all the time, because they're always having a supply. Well, your quads, for example, or your vastus lateralis, like we've been talking about, it can fatigue out very quickly and you have to rest and recover eventually at some point because those hundreds of fibers that are innervated by the one motor neuron or the motor nerve will get tired quickly or at a certain rate depending upon how fit you are. And that becomes a concern, and that's why we have, that's why when we work out, we can sustain more effort for a longer period of time because we're not as fatiguing as we were. So with the neuromuscular system, there is something called the all or none principle. And the all or none principle basically means that either all or none is going to happen. There is no in between with the neuromuscular system. If a nerve sends an action potential, you will get all. If a nerve is stimulated, it will send the signal and it will send it as strongly as possible. If you have no innervation or no action potential, then you will have none, or you will have no contraction that happens because there is no stimuli that has occurred at that point. So all or none, either it's going to or it's not going to. And that's the key, is that, if a nerve sends an impulse and an action potential, it's going to create a contraction. So whether it's involuntary or voluntary. And we all know the difference between those, where if you have a muscle spasm, that means all is happening. Whereas if the muscle is relaxed, that means none really is happening, to an extent, because we still have to have specific contraction occur at certain areas when needed. But if you have if you have like an involuntary spasm, that's just the nervous system sending signals. And you're basically going to get that because we can't once the action potential is granted, you can't shut it down. Unless obviously the nerve becomes severed, then that's a whole nother story. So when we talk about that motor unit, we talk about twitch or twitch summation or tetanus of a motor unit. And if you notice, a single twitch is the A, and then B is the force resulting from the summation of two twitches, so bing, bang. And then you have what we call unfused tetanus and fused. So you can see here where as force goes up, more frequency will occur because you need to have a constant stimulated motor unit to provide you with constant effort or movement. So the motor unit will become fatigued based on the amount of force and the frequency. And we try to, depending upon the movement, try to sustain as much as we can before either failure occurs or we can finish the end of our whatever we're doing working out wise, that we can work with that. So I was talking about type 1 and type 2 before. Understand that you have, with the neuromuscular system, you have the same types. You have type 1 and type 2 motor units, but you also, with the muscle fibers, have type 1, and then they kind of break it down a little bit deeper into type 2 and type 2X. Type 2X being the most explosive, most rapidly available muscle fibers that you can get in an explosive state. So, how does it typically work though? Well, type 1 muscle fibers are typically called upon first, but if there is more force production that is needed, the body instantly will shift over to type 2 muscle fibers. And that's how you get that call to action. So, type 1s, they will make the effort first, but then if they cannot sustain, they will call upon type 2 very quickly so that you do not lose out on whatever you're trying to do. So looking at everything here, pay attention to these left side characteristics. I'm not going to go through them all, but pay attention to them and see the main differences between the type 1, type 2A, and type 2X. Type 2A being more hybrid, they have this potential to be very, very explosive, but also have a little bit of that aerobic capacity in them as well. And that's why you see a lot of intermediate in there. So just pay attention to each one of those and understand what each one is trying to say in that process. So what's the takeaway here? Motor units are composed of muscle fibers with specific morphological and physiological characteristics that determine their functional capacity. Hence, this chart right here. So you need to make sure that you know the differences between them and what those differences are. Motor unit recruitment patterns during your exercise, we kind of hit on that a little bit. Type 1 first, followed by type 2. The force output of a muscle can be varied through change in the frequency of activation of individual motor units or the change in the number of activated motor units. So the recruitment patterns are going to vary depending upon what the needs of the body are and what is being called upon. So if you start off with something that, just say you're lifting weights and you start off with something light, well, your motor recruitment pattern will be minimal compared to as you start going up in weight and dropping the amount of reps you're doing. So you can see here that you're going to start calling upon more as more force production is required. And that typically is the rate that you're looking at in terms of intensity. So we want to pay attention to those aspects as well. So the more force that's needed, the more recruitment that's going to be required of motor units and the repeated push of them. And that's why if you try to do too much, that's why you start getting that fatigue feeling, especially when you start working up at those higher percentages and you're trying to, just say you're trying to work at 85% of a maximal effort. Well, you're going to eventually hit a point where motor recruitment patterns are high, but you're in a fatigue state because you cannot withstand that force over and over again, and your ATP stores are becoming taxed, neuromuscular effect is getting taxed, so your nervous system is becoming fatigued, and that's causing a fatigue in your muscular system as well. So you have to look at all of these aspects to really understand that recruitment patterns really do make sense, and that it's going to, the frequency is always going to change depending upon what you're doing. The body always tries to do the most efficient way, but when you make it not efficient to eventually make it more efficient, I know it sounds kind of weird, but the process will eventually pay off, and you'll start to see the changes in how the body starts working easier, more efficiently, when it really used to work harder for less work, which we don't want to have happen. So what are our takeaways here? Force output of a muscle can be varied through change in frequency of activation. We just kind of hit on that. Also understand that we have proprioceptors that sense change, and that cause that once that change is sensed, it'll start to provide the central nervous system, the brain and spinal cord, with information that will change the amount of muscle tone that is needed, and it will allow you to provide more of an effect on really making more of a conscious effort on completing complex coordinated movements better. And that's really what happens with the next section here with our proprioception, or basically understanding where the body's specific task in space. Well, based on what this says here, specialized sensory receptors, we have two major ones. We have muscle spindles and we have Golgi tendon organs. Muscle spindles are located directly in the belly of the muscle, and what they do is they detect stretch, excessive stretch, so that you can then activate sensory neurons that will then send impulses to the spinal cord, and then from there, it will release information from the spinal cord to outward via the motor neuron and then cause a change in the muscle to contract, to relax, whatever is being called upon. So basically, what happens is it's this vicious cycle. You have the muscle that stretches, right? The muscle spindle that says, no, I don't like this. And it will send out a signal via sensory neurons to the spinal cord. And then from there, it'll kind of be like the brain center and be like, I don't like this. It'll send a signal out via motor neuron back to the muscles, and then from there it'll say, don't do that anymore. Like, just say that you're stretching, you're sitting on the floor trying to reach out, touch your toes, you can't reach or touch your toes, but it's starting to hurt. Your body naturally detects this via muscle spindles saying you're stretching too far, stop it, here's why, and it's going to send a signal, and from there you're going to pull back. On the other hand, Golgi tendon organs, they are a detector of basically extra stress or tension that is felt within the muscle and the tendons. So typically, what will happen is when the load of something becomes more extreme, the Golgi tendon organs will sense that. They'll send a sensory input out via sensory neurons back to the spinal cord. Detection is made, motor neuron output to the muscle, and it will change the contracting mechanisms of that same muscle. So that happens very quickly. This isn't something that just like, oh, let me think about it. I'll send a sensory neuron, I'll send a sensory signal now. Sensory neurons take it away. No, it's happening like instantaneously, um, in a way that it sends feedback very quickly and it sends feedback back to the body very quickly. So it has to happen very quick, or what are we going to end up with? Injury. So what do we want to say here? Muscle spindles located in the muscle. What do? They detect stretch. Golgi tendon organs located in the tendon of that muscle, and potentially along the very fused areas, the extrafusal areas where the tendon meets the muscle. That's where it can also be located as well, but typically it's in the tendon. And what's its job? To detect tension, or to basically detect, um, high load tension. And there they will basically save the body and be self affecting. It's kind of like, you're trying to always make sure that the body is self preserving itself so it doesn't hurt itself. So, what do we do if we want to incorporate more of this improved force production? Well, we got to do a few things. Heavier loads obviously will help make sure that the nervous system is channeled correctly. If we want to improve force production, we know we're going to have to increase the size of the muscle, the cross-sectional area of the muscle. And we need to be able to make sure that we use the right types of movements, like it says here, multi-muscle, multi-joint exercises done explosively, so that you can call upon fast twitch fibers quicker. Remember, we said type 1s will be called upon first, but we want to switch that over very quickly. So if we train to improve force production, we're going to train in an explosive manner to offset that. So moving out of the muscular system into another type of muscle, the heart, all right, we want to make sure we have a cardiovascular understanding here. So we know that the heart, really it's got two sides to it, and it's got four chambers, two sides, the right and the left. Now, the right, what they say, right ventricle pump is its job, or the right ventricle versus the left ventricle is, those two areas on the bottom of the heart, the right and the left. The right ventricle will pump blood to the lungs, the left ventricle will pump blood to the rest of the body. The upper chambers are the atrium, and the atrium will allow blood to be sent back from the lungs and back, the left atrium will get blood back to it from the lungs, and the right atrium will get blood back to it from the rest of the body. And you're always having this constant flow. So really what you need to see and follow are the arrows within the image right here. Follow the arrows and it will show you. So if we typically talk about it, it's right atrium receives the blood back from the body. Now, what happens is that blood is then pumped into the right atrium. It gets pushed through, or from that pulsation of the heart, the beat, um, from the right atrium through the tricuspid valve into the right ventricle. The right ventricle will pump, send blood out via the pulmonary artery to the lungs, where it'll get oxygen from you breathing. It will rejuvenate itself with oxygen, and it'll get sent back to the left atrium by way of the pulmonary vein, because veins bring blood back to the heart. And from there, the pulmonary veins supply the left atrium with the blood. It will get pumped through the left atrium through the mitral valve or the bicuspid valve down to the left ventricle, where the heart will then beat again, and it will allow, and not that there's two separate beats, but you have two releases at one, for one beat. And with that left ventricle, the blood being pumped out will then supply the rest of the body by way of the aorta out. And then from there, it'll return back just like it would. And it's just all, again, another vicious cycle. All right. So it's always working through. Follow those arrows and it'll take you right through where you got to go. So with the valves, right, we talked about the tricuspid valve and the bicuspid or mitral valve. You also have the aortic valve, you have the pulmonary valve. All these valves are needed so that you do not have regurgitation or backflow of blood into those areas. That can cause massive problems in circulation. So you have these valves. Also, you have a conduction system. You have you have this way of electrical current causing mechanical contraction of the heart. Now, if you ever talk about lub dub, right, that's what we refer to with lub dub, is you have those two beats with one beat of the heart, lub dub. And that's because the electrical conduction is making sure that you are, you're in the proper rhythm. That's number one. And really it's more for the fact that we want to make sure that if it's too close, we can have arrhythmias, and that arrhythmia can really become a problem. So what do we got to worry about? Well, in this sense, with the electrical conduction, you have your SA node and you have your AV node. Your SA node is your sinoatrial node, which is basically the pacemaker of your heart. It will send, when that node has a conduction system, it'll take the SA, it'll take the sinoatrial, so the atrium will beat, and that will allow blood to pop down to the ventricles. From there, the AV node will send an electrical signal down to the basically the lower portion of the atrium and the rest of, and then the ventricles, and that will allow blood to be pumped out into either the aorta for the left ventricle or to the pulmonary artery for the right ventricle. And that's how you would get blood to start from the top down to the bottom, by way of electrical current sending beat patterns to allow mechanical, contraction of the heart, and basically have this really violent twisting that really occurs with those two beats. It really is. It's almost like wringing out a paper towel or a towel that may have been soaked because you forgot to pick it up off the sand at the beach, and it's just a ringing effect. And you're really trying to get that to really work as hard as it can to provide this pushing of blood as hard as it can. So how do we know about this? This conduction part. Well, we have proper rhythm and we have proper conduction. Well, what do we know about it? We know that there is, sympathetic and parasympathetic, transmissions that are occurring. And that really becomes more challenging because with sympathetic, you're trying to excite, and with parasympathetic, you're trying to relax. So If you're talking about bradycardia, all right, we're talking about lower beats per minute. Understand that people can have bradycardia and be healthy. Just because it says here it's 60 less than 60 beats per minute, well, if your resting heart rate is 55, well, then that means that you're not sick or anything. It just means that, or you have some sort of issue with your heart. It just means that your body is able to pump more volume on a lower amount of effort. Tachycardia being over 100 beats per minute, well, that's the same thing. But that's more of a problem. That's more problematic. Tachycardia, especially at rest, if your heart rate is over 100 beats per minute at rest, that's just too much work for the same amount of intensity that somebody is doing at half the work. So we have to pay attention to that. The more fit you get, the more exercise or even just general movement that you do, the more that can be offset. But always remember we have a proper conduction and we have a proper rhythm. Well, the rhythm comes from an EKG or an electrocardiogram. And this here is how the heart would beat in its own way. Each of these raises indicates a change in the electrical or the electricity components of the way that the heart beats. So when you look, at the P wave, the QRS complex, and the T wave, all of those indicate a specific jump in electrical activity that will either allow for excitation of specifics. So the P wave would be the excitation of the SA node, and then the QRS would be the AV node excitation, and then the T wave would be just a relaxative bump, so that, or indicator that would allow you to be repolarized. So all of these this is in a natural format, and as long as you're seeing a very similar pattern, then you know that your heart is in good rhythm. Now there are, arrhythmias. And it doesn't have to be exact each beat. Now there might be slight variances in those beats, but as long as they're within the same pattern, that means that your heart is in good rhythm. It would have to be very much contraindicated. The indicator of those bumps has to be very distinct, that you can see that there's a very problematic rhythm of the heart and that you have to get help for that. So with the cardiovascular system, once we get past the beat, well, what happens? Well, we have to have the blood vessels take everything to go where it's got to. We already talked about the pulmonary area, where the pulmonary artery takes blood from the heart, brings it to the lungs, where it becomes infused with oxygen. That oxygenated blood gets sent back to the heart to be pumped out to the rest of the body, so that it can be used effectively, so that we can distribute oxygen, so that we can make proper energy conversion throughout the body and basically sustain what we're doing. So the arterial system, like it says here, carries blood away from the heart. The venous system returns blood back to the heart, so arteries and veins. Capillaries are our area of transmission or transfer of nutrients and gases. So whether that be oxygen, or carbon dioxide. So there they are: arteries, capillaries, veins. What is their job? That's their job, is to carry blood either to or away from the body, or make transfer points via capillaries. Capillaries are the only ones that allow for diffusion or passing of things to and from them. Blood, on the other hand, it has a lot of various aspects here, but for the most part, hemoglobin transports oxygen and serves as an acid-base buffer. Specifically, when we start getting crazy in terms of like lactic acid and the buildup of it, how we become very acidic, the blood has to transfer it somewhere to be removed. And then red blood cells help facilitate both oxygen delivery and carbon dioxide removal. So very, very important for that as well. So, takeaway, we talk about, I said it before, transportation of nutrients, waste product removal. That can help with a proper environment that the body can function within. And then blood transports oxygen from the lungs to the tissues, like it says here, for the use of cellular metabolism or to use for energy. And then it transports carbon dioxide from the tissues to the lungs, where it can be removed out of the body via our breathing. So very, very important for that buffering system as well. Then lastly, gross structure of our respiratory system. There's our lungs. There's the arteries the arteries and veins that are there to take blood to the heart and away from the heart. There we go all the way from the mouth all the way down through the vocal cord. There's the trachea and the esophagus, and then there's all of your tree tree bundles. Your bronchi, your bronchioles, and then your the air-filled sacs of your alveoli. So definitely pay attention to those areas. Make sure you can, if you had to, but if you had to answer a question, basically make sure you can label the way that the air flows through the mouth, down through, past the larynx and from the pharynx to the larynx, down through the trachea into the, by way of the bronchi to the bronchioles, then to the alveoli. And that really helps to just kind of drive the air into the lungs so that we can then get oxygen to the blood to then send it back to the heart to then provide it to the rest of the body for cellular metabolism. That's what we're looking to do here. So there's our exchange of respiratory gases, the exchange of air, which we talked about. And then you have a couple little things here called, one of them called pleural pressure. Pleural pressure, like it says here, is the pressure and the spaces, that really small gap between the lung pleura and the chest wall. And that pressure is what helps to maintain the lungs being inflated and deflated without losing the whole aspect of your lung, the structure of your lung. Because that's really important. If that pleural pressure changes drastically, that's when we start talking about like collapsed lungs and, obviously having very severe issues within the body. So that pleural pressure must stay at a constant as much as possible so that when air comes in, it changes the pressure, which allows the lungs to fill, and then the pressure will change slightly to allow the air to be released and recoil as needed. And then lastly, the last slide of this grouping, the respiratory system with the alveolar pressure within the alveoli will allow, basically this exchange to occur of air going in, air going out, whether it be via oxygen coming in or CO2 going out. So without the pressure in that alveoli being below our environmental pressure, you would not have a filling. Remember, items always move from a higher concentration to a lower concentration. So because of that, if we have the same pressure inside of the alveoli that we do with the environment, you're not going to have a change in air. If we have a adjustment where the pressure decreases within the alveoli, that allows basically the floodgates to open so that air can come in and into the alveoli so that you can then have that change. Well, then what's going to happen? Well, when air recirculates and CO2 comes back to the alveoli, there is an increase in pressure above environmental, which will allow the release of CO2 out of the alveoli, and then you will breathe that out as you go. So there always has to be this change in pressure to allow for things to move from high to low and, at all costs. So without that removal of CO2, our bodies will just not be able to function correctly. So we have to make sure we understand that. And that's why diffusion is so optimal, is transferring from those capillary beds to wherever, whether it be muscle tissue, whether it be organs, whether it be, at the alveoli level. It depends, and we always have to have a high to low concentration gradient that will allow for things to go from inside to out, and then that will change the internal pressure of the structure, and that will allow for whatever waste byproducts to go from outside of back into the capillary. So there's always that adjustment cycle. So this is our chapter 1, a lot to digest. Structure and function of the body systems, it really does take a lot. So understand that things are going to be kind of on this review base for the next few chapters. So just keep pushing through, keep reviewing, and if you have any questions, please feel free to reach out. Again, like I said, this is a new set of videos. We were working with the NASM information previous, but it was time. It was time to make the switch, and that's already been uploaded. Now it's time to work with the NSCA stuff. So Again, leave questions inside of the comments, and I will continue to produce these videos as best I can. The other thing too is, feel free to, donate. If, I'm not a big salesperson in this regard, but please feel free to donate. You know, you're more than welcome to leave a thank you. And then there's a donation part that you can do, and it comes right to me so I can do more of these videos. And I can also take the time to be able to potentially, purchase new equipment that can allow better, recording versus just me on my computer. But again, any help is always welcome, but don't feel like you have to, even though it can go a long way. So I hope you all enjoyed this. I hope to hear from you in terms of questions or concerns, and then we'll go from here. Chapter 1 done and complete. Let's move on to chapter 2, and let's just keep reviewing as best as possible. So have a great day. This is Dr. Jeff from the Exercise Science Institute. Feel free to, like my Instagram stuff, my Facebook stuff, whatever you want to do. But love to hear from you. Take care. Have a great day.